Thank you for joining today's webinar, Guide to Parallel Computing with Julia. My name is Sanjeev Dasgupta, and I'm the Marketing Manager at JuliaHub. This webinar will be led by Jacob Wawarka and Dr. Jeff Bezanson. Jacob is a JuliaHub and JuliaSim sales engineer and comes with an extensive background in mathematics and building application in high-performance computing environments for production-ready automotive workflows. As many of you might know, Jeff is the co-creator of Julia programming language and co-founder of JuliaHub. With this, I'll hand over the session to Jacob and Jeff.
Parallel computing, it still does at MIT. And so it's something that we've always been trying to do and trying to find new and better ways to do it. And now on JuliaHub, we kind of have the hardware to go with the software, all the parallel computing capabilities in Julia.
All right.
Please take it away, Jacob. Thanks.
Yeah, with that, we'll get started. And that speaks to the motivation of how a lot of this work has gotten us to where we are. And in particular, what we want to do is introduce some of these built-in features of the Julia language so that you can start to understand how to optimize your own workflow, take better advantage of these more high-powered machines that we have access to. And then we're also going to take a look at JuliaHub, not only for exploratory analysis, but also some mechanisms that we can use to scale these jobs and run in batch as well. And in addition, additional motivation is some of the recent efforts that have gone into providing more documentation, more resources to help get you started using Julia efficiently. So this goes with a recent blog post on our website, and also a white paper that is going to delve through some of the same topics. So if you prefer PDF you want to read after this, or maybe you've already seen it, it's a good reference for future work. Both of those are here. And then at the end as well, I'm going to include, there's a lot of great resources going back to some of the original blog posts where Jeff introduced many of these features and concepts. As well as a previous webinar that worked with similar problem and kind of dives a little bit deeper into what's happening. We're going to look at a basic workflow. This is going to be a really basic data science workflow where we load some data, we do some processing, we get some results. I'm going to take a lot of liberty with this. I'm going to gloss over a lot because the particular data science type things that are happening may not be of interest to you, but hopefully you join so that you can start to, you're interested in learning more how to leverage some of these parallel computing paradigms in your own work, your own programs. So we're going to take a look at what those are, when to apply them, and then what the Julia mechanisms are, what Julia provides in order to run these types of jobs. And so with that, we're going to just go through a real fast crash course. Like I said, for more detail, the white paper on the JuliaHub website is a good resource. And then of course, you're never going to beat the Julia manual as well. There's many sections on parallel programming. But for the crash course, so we're going to look at 3 types of parallel programming: asynchronous tasks or coroutines, multi-threading, and distributed computing. So on the left, what you see is a function. On the right is that function being called sequentially. We can use this example to start thinking about asynchronous tasks or coroutines. So what's happening here shouldn't surprise you. The sleep in the long process, you can let that represent some long computation that takes about 3 seconds, and then at the end it returns your result. And then when you call this sequentially 3 times, the runtime stacks up. So that is pretty typical when you're doing exploratory work, maybe getting programmed to work for the first time. And it's okay, but what we really want to do is overlap these executions to make better use of our hardware. And also just kind of a note, technically this is a concurrency pattern where we're dealing with many things at once is kind of the way to think about it. So what Julia offers us to handle this type of problem are tasks. So we can take that same function, wrap it in a task, and schedule it to be executed. So what you see at the bottom of the begin block is just fetching all the results. So once the task is complete, we can get that result. And so functionally, it's no different from what we saw before. We can run these tasks, schedule them, but the overall runtime is now 3. And it's 3 because that's about the same, that's about the time as the longest running process. So let's just say that there was some variance in these. One took 5 seconds and the other 2 took 2 seconds. It would take you about 5 seconds to complete because that's the longest runtime. So tasks is the mechanism that we use to overlap the execution. And this feeds really nicely into the next mechanism I want to talk about, which is the threads.atSpawn macro. So taking the same structure, right? Same function on the left, on the right. Now we're calling that function 3 times, but we're prepending threads.atSpawn to the function call. So atSpawn is going to produce and schedule a task on some available thread. So a thread here is a sequence of instructions to be executed on some core. But notice that we really don't have to worry about tasks. We don't have to deal with the scheduler. We can just throw spawn in front of each function call, and all that's really handled for us. At the end, we fetch our results, and we still get that advantageous runtime. So another mechanism that is a little, I would say, for maybe a more simple use case is the threads.atThreads macro. So if you have a for loop, because essentially we did here, I could have changed this begin block to say, for 1 through 3, run a long process. And that's what we're seeing here, except for now I prepend that for loop with the threads.atThreads macro. And so now we have this really powerful abstraction. Again, we don't worry about tasks and schedules, but it is going to handle that for us. So it produces and schedules a task on an available thread. And really the only thing that you have to do is make sure that Julia knows how many threads it has available. And we'll talk a little bit about how you do that. But it's a really nice, simple way to speed up some of these for loops. For more fine-grained control, we'll probably revert back to spawn, but this is still an important one to see. Now, one difference here is the results. So what happened to my results? When I was creating tasks, or spawning them separately and fetching the results. That's a little bit harder to do in this simple example. This is where channels come into play, and we're gonna take a look at that in the example. But a channel is really just simply a pipe, so it can connect, 2 distinct sets of processes. So 2 distinct processes. Data can flow from one end to the other. So one process can feed data into the channel and another process can take data out of the channel. Between tasks and channels, there are really powerful tools to accomplish a lot of various parallel programming patterns. So we're also still in concurrency land. We're not necessarily talking parallel just yet because true parallel execution occurs when we're carrying out these tasks on their own. Each task is executed on its own core, right? This can be really effective, but can also be really tricky. Thankfully, the Julia language offers a standard library that we can load called, so right there at the top, it's using distributed. And this is gonna make the process of leveraging multiple cores much easier. So first we load the standard library, and then we have to make one more change. So that long process on the left that we've been using this whole time, we have to make one change to that now. And we have to just make sure that every worker node is aware of that function, because we're going to ask each one to run it. So they have to know its definition and how to process it. So we prepend our function call with the @everywhere macro. Otherwise, it's functionally the same, right? And now I can run a for loop. I can run that iterative process, and each one will be executed on its own core. I can optionally include a reducer. So that's what you see just to the right of at distributed, the addition symbol in parentheses. So that's going to run our long process 3 times. It's going to wait for all of them to complete. It's going to take their results. It's going to reduce them down to a single number using the operator that we define there. So that really takes the process of how, I have my code. How do I get this running on all these different machines that I have available to me? How do I get the results back? How do I aggregate them? This can be a really nice tool. The syntax is not too verbose, but offers a lot of flexibility there. So there are other methods. There's something called PMAP. We can maybe get into that a little bit if people are interested. But typically speaking, this is really the easiest way to get started. This is where a lot of the power I feel comes from, because with really minimal changes to your code, you can start leveraging better hardware, more better hardware. So I covered the 3 kinds of parallelism. And I think that the question most of us would ask is, can you combine all 3? And the answer is yes. It'd be great if we could. But the answer is not. I guess the answer is it depends. It's not always yes. We have to consider the problem at hand and how our problem lends itself to each one of those different approaches. So now you've seen the Julia syntax, and you have an idea of how these things work. But we still need to talk about how you decide which parallelism approach fits your problem, and the kinds of questions that you want to ask when you're figuring this out. First and foremost, if whether or not your program is correct. So is everything working correctly? And only then can you really start to break this down to leverage better, leverage hardware more efficiently. And the next question is to identify what resource you're limited by. So is your problem CPU bound, memory bound, so forth? That's a big determining factor, because that is going to give you a clue as to kind of where you should start looking. And then you also want to identify which individual units of work can be done in isolation, because these are going to translate to our tasks. So what things rely on no global state? They don't have any. They don't have anything externally that is trying to access the same data or write to the same place on disk. I mean, there's a whole lot that can go wrong. You're looking for things that can be done in a silo, essentially. And that is what we're going to take a look at. And we're going to do that, again, by taking a look at a basic data science workflow. In particular, we're going to look at data processing, data loading, and data processing. And we're going to ask each one of these questions on this problem and see how we can use those mechanisms that I showed. So now you should be seeing my Julia IDE. So just I guess a quick note, this is running on JuliaHub. So it's VS Code in the browser. I have access to the standard VS Code environment that I probably have installed locally, like many of you do. But additionally, I have the nice benefit of being able to run jobs in batch. So I can perform my interactive exploratory workflow here. And then whenever I'm ready, I can take that code and run it distributed on any arbitrary number of machines, and I can control their configuration and so forth. So first, we're going to just take a look exploratory. We're going to kind of talk about what we see. And to describe the problem, I am going to, like I said, gloss over a lot, but essentially what we're going to do is generate some data. And I don't really want you to worry too much about how this data is generated, but I will show you a sample. So we're going to generate some sign bundles, and to make them slightly more interesting, they're shaped by this modulation curve. They're not perfectly centered around 0. There's a lot of noise. So it looks like something that maybe is representative of some data that you work with, but regardless, it gives us now something to work with that we can start using to process this data. And
can you make it one click bigger?
Yes, I can. How's that?
Thanks.
No problem. So the other thing to note is that there are 2 different batches. So I have one batch that's 200 samples. So I generate 200 CSVs, and these 200 CSVs contain these different sign bundles. We're going to work with this interactively. And then I also ran some benchmarks with 2000. And the reason being is that once we apply our parallel programming techniques, we want to know how it scales. So we hope that on large data, we gain even more performance. So we'll see whether or not that's the case at the end. And this is most likely a pretty typical way to go about your work. You're going to, not necessarily take on the ocean all at once. You're going to break down your problem into, maybe a smaller bit. And it's a good way to make sure that your program is working as you expect. So this is the data that we're working with. And our serial run, you can see here. There we go. Let's make a little bit more room. So I include some common code. There's not too much there. We can dive in a little bit if needed, but really all it does is it provides me with these 3 functions. And these 3 functions correlate exactly with the simple diagram that I shared in the slides. We want to load our data, we want to process our data, and we want to plot our data. Now this is the processing the data is doing some pretty standard things from multivariate stats package. It's going to run a principal component analysis and fit our data using that, and then it's going to take a sign bundle, and then it's going to look for its best pair. So this is an example of a result is trace number 118 is best matched with 135. Now, all of this is done in serial. We've set it up that way. And so that's kind of our starting point for this is essentially as simple as the program can be from a parallel computing standpoint. Where do we go from here, and how do we start to accelerate this? So first off, let's just run this through. I'm just defining where my data can be found. I'm going to process my data. I'm gonna perform one run to process the data first, and that's to make sure that that function is compiled, so that when I do run this this block here with the elapse macro, I want to make sure that I'm timing. I'm not including the compile time because that wouldn't be appropriate for what we're measuring. So this elapsed macro is going to help. It's going to put the timing that it takes to run this, and it's going to put it in this variable, and then we're going to use that to put a nice info message out, log an info message out about how long this took. And for every file in our set, we're going to load, process, and plot the data. And you can see, because I have another logging info macro here, I can see that it's processing each file in order. That's because we sorted it at the beginning. So it's going to go through, and it's going to, for everyone, load the data, process the data, plot the data, move on to the next file. The secret is that this is, even though we're trying to set this up as serial, is not as serial as we think. And that's because especially when you start to include code from packages and such, some of them can benefit from some optimizations, such as BLAS calls. So the PCA function from multivariate stats is one of those. I'll show you a screenshot later. We can see that this doesn't necessarily correlate with what you think, where this is just pinging one thread, pegging it until it's done. It is actually distributing a little bit of the work to some other threads. But generally speaking, this is as close as we can get to being serial for this case.
CSV parsing is multi-threaded, isn't it?
It is. We have turned that off for now, just to, again, make this as, sorry, I think it's,
yes.
Oh, it's in common. I'm sorry. Yeah, we've turned that off on purpose just to just to simulate this running in serial. And so when I read this CSV into a data frame, I'm using the end tasks keyword argument, and I'm just telling it to only run on one task. We can raise this. It will take advantage of more. However, by doing it this way, we're gonna later take fine-grained control of when these get loaded. Good point, though. Okay, so that's what's happening in serial, and let's scroll over. Here we go. So now what we're going to do is think about how this is broken up, right? So if you take another look at this for loop, there is no extra data needed to process each file. That file is the only parameter essentially to everything else happening here. And so that means that it's most likely a good candidate to become a task. In other words, it's something that I can isolate the execution of all of this for each file on its own thread. And by doing that, I may actually overlap the overall process for each file. And that's going to be it's going to be preferable over doing each one in sequence, like we saw happen here, as evidenced by all the info messages, and it's happening one by one. And so, like we showed in the slides, it's really pretty simple to achieve this with a simple for loop like that. We're going to use the threads macro, and that is the only change here, except for this results array. So again, this is a good part of identifying where something's appropriate and where something's not appropriate. I want to run at each of these on their own thread because I think that this work can be done in isolation. However, it's also important to note when this can't happen. So in this example, I'm using the Plotly.js backend. I know GR suffers from this. Some others do as well. I don't know which plotting backends are affected or have solutions to this. But essentially, plotting backends typically don't want to work nicely with plotting, rendering multiple plots at one time. And so when you do this, it'll either error or it'll just kind of give you a warning and say, that's not allowed. I'm going to process these one by one. You're not going to get the benefits of running these on desperate threads. So what we're going to do is separate out what we can run on different threads and what we can't. So the plotting data is going to be done at the end, but we're going to prepare the results. We're going to process all the data on different threads and push all of those onto this results object. And then when we're done with the loading and the processing, we're going to go through and we're going to plot each of them because we know that's going to be safe for our plotting backend. And up here, we're going to be opinionated. We're going to not let you run this if you're on different threads because you're really going to see the same thing that you saw previously. So make sure that you let Julia know that this should be run on different threads. And here, this is referencing the -t flag. So when you're starting Julia, you can either do -- threads and provide a number or -t for short. And when you're working in VS Code, there's also a setting that you can set. So here it's a environment variable. It's going to be essentially you set this through the VS Code settings, and you can either provide it a number or you can say auto, and it'll just work with however many you happen to have available. When you're working on JuliaHub, this is done for you. So thankfully, we don't have to worry too much about that in this example, but it's worth mentioning if you're going to run this on your own on your local machine. So am I running with one thread? No, I can continue and make sure that my process data function is ready. And then let's run this loop now with the loading and processing distributed across threads. So already you can see a difference. This isn't running sequentially. And that's because it's breaking up the work that it has into about the number of available threads that it has. And so really it just takes whichever one is available at whichever time starts working. And then as soon as a thread completes, it's going to raise its hand, say, I'm ready for more work. And if there's more there, then the @threads macro will create a new task, schedule it for that thread, and it'll execute. And then again, here at the end, all of the plotting was saved until the final step. And we see that the finished, the final product is faster. So I have some result slides. Numbers are going to vary a little bit. So don't worry too much about keeping these numbers in our head, but this is kind of the lowest hanging fruit for how we can get back some performance on this problem. And just with this, I think, pretty good. Like I said, minimal changes to the code, already gained a lot of performance. I think it's, not quite half, but good performance outcome there. I guess if I scroll up, I can see. So it was about 1.5 seconds per file before, and now we're 0.6, so pretty good. But can this be improved farther? And the answer is yes. So I mentioned this @threads macro being really good for kind of the simple use case. That's what we explored here. And now to take more fine-grained control, we're going to use this run threaded workers. So instead of only threading that one loop, what we're going to do is we're going to break down that problem into different processes, different tasks. We're going to utilize channels to feed data to those different processes whenever they become available. And the result is going to be that we leverage more of our threads, more of our resources, more often throughout the workflow. So let's walk through, look at how this is going to be accomplished. Again, make sure you're running on more than one thread. All of this is going to be the same. So before we execute, let's just walk through bit by bit. So we're going to hit the starting time so that we can compare against it later. So next, we want to first read in the CSVs. So we're going to take that first portion of loading the data, and we're going to put all that data that we load into a channel. Now remember, a channel is, you can think of it as a pipe the data flows through. One process is going to put data into the pipe, and another process is going to be waiting for data to come out the other side so that it can perform its tasks. And here we are going to create as a channel with the size of which is as many threads as we have available here. So you can see this signature channel, squirrely brace, any, and then 8. So 8 is the length, any is the type. You can restrict the type that is allowed in this channel. We're not going to do that here, so it defaults to the any type. And then this data in channel is going to be populated with this put bang function. So what we're doing is we are spawning some different CSV loader tasks, a CSV loader task where we load the CSVs as fast as we possibly can. We're going to run this threads macro inside the spawn macro. That's legal. We're going to load the data. We're going to put our file and our data frame into the data in channel. And then we're going to give a nice little logging message so that we can kind of see when we're done with all that work. Once we're done, we're going to close the channel. So that takes care of loading. Now what about processing? So we want to process the data as they arrive. So we have a results channel, and we have this task data processors object here, this array. So it's going to be a list of tasks. And what we're going to do is for every thread that we have, take that data from the channel and then essentially perform the data processing, really just as we did before. And just as we also did before, when we pushed the results onto just a simple array, we're just going to put those new results onto our results channel. So this is really almost identical to the for loop that we had before. We just do one extra bit here at the end where we build up a list of all the data processor tasks. And the reason is we want to keep track of which ones are done so that we know when these channels can be closed. And that's what you see here. So this task result closer is gonna it's gonna make sure that when you're reading the data in, writing to results, we only close the results channel when all the processing is done. And so we use this wait function. It is broadcasted over all of the tasks in this array. And when that's done, we're gonna, again, log out a nice message and say that, this is, this program is now finished with all the processing, and we can close the results because we have everything that we need, close the results. And then finally, on the main thread, just as before, we can plot. And the reason that we're going to do it this way is, again, because the plotting backend typically makes this a good idea to do. The difference is that we can take results as they arrive. So we don't necessarily have to wait until the very end to plot all this data. We can load all the data, process it as fast as we can, and then take the processed data from its channel and plot the data. Plot the data when available. And again, we just wait, make sure that everything is completed, and then we compare the new time against the starting time. And to run this, let's do it from the REPL. So again, I'm on JuliaHub. I can open up a new terminal, and I can say, run Julia. I want to run with this environment that I'm currently in. And I want to run the threaded workers example. So first it's going to load the packages. And then it's going to start loading those data files. Any second now. There we go. So we started that data load task, and then we're starting the processor tasks. We're waiting for results. As each processor finishes it, it sends its results in the channel. So now we're done loading everything. We're just processing and plotting. And we'll wait for it to complete, get the final timings. We're done with all 30 files. We can close the results channel. And we see here that it took about 0.8 seconds per file. So we took really fine-grained control over when data is loaded, when it's processed, and when it's plotted. And these this type of workflow is really powerful when, like I said, when you identify what areas of your program can be separated like this. And this isn't necessarily trivial, right? It kind of takes a little bit of time to wrap your head around tasks and channels and when to close them, when to wait on them. That's okay. Odds are, you have maybe other interesting things to do with your data, but this is going to be a good example for how to think about and break down these problems. And so with this, I think that I would like to hop back to the slides and just kind of talk about what we did. So in the serial run, I had videos here, by the way, but they didn't really render nicely. So you'll have to do with a screenshot and my commentary. But this is a screenshot of the middle of the serial run that we saw. And like I mentioned, one CPU is being pegged. There is some activity on the others. It's not because I have something running, some other program running in the background. It's because multi-threaded BLOS calls were being called or being invoked by the PCA function from multivariate stats. So it's not perfectly serial, but that's kind of what we saw there. And again, that was also the slowest time that we saw. Most of the work was done on a single thread, except for where the BLOS calls were executed. And then we looked at the threaded run. the threaded loop run. So then we split all of the loading and processing of data across available threads. And then the data was plotted sequentially at the end. So we can see we're processing them in different orders, but then they do happen sequentially during the plotting phase. And if you look at the CPU utilization, all of them are activated. So this is looking much better. We're taking better, we're making better use of the resources that we have available to us. They're not 100%, but they're doing pretty good. There's still room for improvement, and that's where we see our last example. So we identified which individual units of work could be split into distinct tasks. We read CSVs, read CSVs and put their corresponding data frames onto a channel. And then we read from that channel, processed those data frames, and put the results on another channel. And then we plotted those results whenever whenever they became available instead of all at once at the end. So the result is more CPUs being utilized more throughout the entirety of the workflow. And this is really, I think, the iterative process of how to get there. You're gonna have to sit there and watch your jobs as you're working on this, and make sure that you understand what your code's doing, what any function calls from third-party packages are doing, and yeah, always focus to make sure that you're breaking this down so that you utilize as many resources for as long as you can. And these are the final timings that I took just earlier. They're going to vary slightly from what we just saw, but essentially the same, right? So small and large represent the two different sizes of data I generated. So one was 200 samples, one was 2,000 samples. And I include both because you're going to see really improved performance in the large when plotting doesn't become the dominant force in the timing. We benefit even more from that work that we did creating tasks and channels and splitting those out across threads. So to summarize, serial was the slowest. It took about 2.6 seconds per file on the small, and then just with the threaded for loop, cut that in half, and then improved it further when we got really fine-grained control over what work was happening. And then on the large batch, again, we see even better gains, almost a third of the time, just with the threaded for loop. And then we cut that down a pretty impressive bit by taking fine-grained control again. So we just talked a lot about asynchronous tasks, coroutines, multithreading. We haven't talked that much about distributed computing, and I want to show, these are screenshots from JuliaHub. I want to show you these because, like I said, we do have some nice facilities in the Julia language. JuliaHub provides a really nice interface for you to submit these jobs. We can take a little look at how you might do that through a graphical user interface as well as programmatically. And this is an example of something I did. I took the same run, I ran it in serial, and I ran it in parallel. And it's just nice to see that you can track your workers, you can see the utilization rise, you can keep an eye on the memory as well as CPU utilization. You can do this real time as your job's running. And then you can also leverage the logging macros to get really detailed information about even the value of certain variables throughout your program. So didn't focus too much on this. However, especially if you have a workflow that is going to benefit from this paradigm and you're interested in seeing more of that, we'd love to hear from you, what you're doing and what good example might be representative of your work. For everyone else is kind of wondering if they should leverage distributed computing. Well, yes, it can be highly beneficial. It can also be a little bit trickier to set up. And without getting into which situations are better for it or less suited for it, I think that generally speaking, a good practice when you're kind of figuring out where to start, is to start with the simplest form. And I think that does include the path that we took today, which is target threads first. And that's going to force you to break your problem down to its simplest form, identify what tasks can be run in isolation. And I think once you go through that exercise, view your timing, try to squeeze the performance out that way, it will start to become apparent when and where distributed computing is the answer. And so with that, I wanted to include some resources. So again, we have a blog post to kind of get you started. The white paper is going to be much of what I just covered, but not really focused on a particular problem. It's going to be more of what we covered in the beginning of the webinar, where we're introducing concepts and some of the syntax and the results of those really simple examples. I also want to point you to a past webinar. So this problem was run through by Dr. Elias Saba, my colleague here at JuliaHub. And he goes through much of the same thing. He talks a little bit more about the source code and what it's doing when it's generating results and processing that data. But mainly he focuses on how you understand how you understand the impacts of the implementation of these parallel programming techniques. And then, as I mentioned earlier, the Julia manual doesn't really get much better. It's going to be the great place for you to start if you are interested in learning more about Julia's parallel programming mechanisms and how everything works under the hood. And with that, it looks like there's about 14 minutes. I think I'll open it up for questions.
Yep. Thank you, Jacob. We already have about 8 questions lined up in the Q&A section. If you see, we can start with the one that came early on.
I don't see it right now. Is it okay if someone reads it, or
yeah,
maybe Jeff, can you see them?
Yeah, if you click the Q&A thing, they come up.
Okay.
All right, so the first one was, why would you go with JuliaHub over Azure, G-Cloud, etc.? So it currently runs on AWS, right? So it does use AWS under the hood. It's just kind of basically a Julia front end to AWS, if you will, and the scale that it provides.
Okay, so I do see. What's the difference between threads and distributed? Are they the same if we use them with multiple cores? So yeah, threads are going to target the available threads on a core. Distributed, typically when we talk about cores, we talk about distributed having multiple cores, and so these are going to be their own machines with their own resources. They may have many cores themselves. I actually didn't get around to showing it, but like I said, we did have a graphical interface right there in VS Code to help you say, I want to run this job in batch, and I want to make sure that the machine it runs on has this many CPUs and it has this much memory per CPU and so forth.
Oh, and in particular, threads is shared memory. So all of the threads see the same address space using threading. So they can communicate just by reading and writing memory locations, and reading the same memory in distributed communication has to be done explicitly. So there are lots of trade-offs.
And I think that question just came in. Can you talk a little bit about data sharing between different processes? I don't know if that came in after your explanation, Jeff, or if that's an additional question.
I think there are a few more questions before that, actually. If you just scroll up, there's something from Marcelo.
So what approach would you take to parallelize a long-running test suite around 1 hour? Assume it consists of about 50 files that can be run independently. Do you have any considerations about sharing compiled code among processes? I'm going to let Jeff take this. I think that we definitely have some insight here.
I seem to see a different list of questions than you're seeing.
Really?
Like I do see a list of
Yeah.
questions, but that one isn't on there. I don't know. I don't understand how this works.
You'll have to scroll up actually. You scroll up, you'll see.
But yes, so we run our standard Julia test suite in parallel. We have for quite a while. So our test package has some facilities for doing that. If you can break it into multiple files that are independent, that's great. Then you can I would probably just use distributed to just run multiple processes at the same time. And let's see. Yeah, what was the rest of the question?
It was, do you have considerations about sharing compiled code among processes?
Oh, sharing compiled code. Yeah, so now we will precompile packages. So I think you would definitely want to precompile packages you're using before running your tests, and that will actually cache compiled code from all of them. And then each process that starts up to run tests will not have to compile it again. So by factoring things into packages and precompiling them, you'll be able to share and reuse the compiled code. Okay, this is a good question. Can you use the push bang function in parallel or dict? So the array and dict types are not automatically synchronized. So if you want to use those for multiple threads, you'll have to do some synchronization. So we have you can use like a lock, for example.
There are a few more questions above. One of them is, how do you know which processes should or should not be parallelized or threaded? I'm referencing your conversation about now threading the plotting.
Yeah, so some operations are going to be inherently serial. This is something that you would, so take the plotting, for instance. This is likely something that you would find out in your exploratory phase when you're working interactively with the REPL, because I believe that if you do try to render multiple plots multi-threaded with, say, the GR backend, then I think that it's going to complete its operations, but it's going to give you a warning and saying that I see what you're trying to do, but unfortunately, I'm not able to support this. And so it depends on the package a lot of times. Sometimes it may involve digging through the source code to understand what's going on. Sometimes, in the case of plots, it might handle it a little bit nicer and kind of be friendly, letting you know what's allowed and what's not allowed. And that's ideal, but of course, not always the case.
Just beneath that, there's another question from Scott. He says, Jacob, so when you took fine-grained control, your time per file went up, not down, even though you parallelized the data loading and plotted results as they became available, as opposed to threaded processing alone. Why?
I guess I wasn't paying as close attention to the number as I was before, but I can tell you that on the many runs I've done myself, that was not what I saw. So I am not sure how to respond. I think, yeah, I guess it's a good time to mention that this repository is available. It's public, and so yeah, it'd be good to run this on your own and see if you can make sense. First reproduce that timing, and then make sense of what's happening there, and let us know how to improve it.
And yeah, there are a few more questions. I'll just going through the order they came in. We don't know. Okay, it says, hello, thank you for your presentation. My question is, what is your suggestion for method to compute cross-checked events? To check whether two entries have crossed time and distance.
I'm sorry, I do hear you. I was looking for the question and also trying to provide the link to the repository, and I'm afraid I didn't quite catch that.
Yeah, so if you scroll up, you'll see all the questions that came in order actually. Just to scroll up the Q&A window.
Oh, it seems like kind of an algorithm question. Yeah, I don't know. It's a little bit. It seems like it's a little off topic.
Okay, there's another question that says, can you talk a little bit about data sharing between different processes?
So in the case that we just covered, that was where the channels mechanism came into play, right? So it's how we separate our tasks and push data between them, so that when it becomes available, some work can be started. And then, as Jeff referred to, when you're running this in distributed, there's a lot of different, I think, trade-offs and other decisions that you have to make about most likely. So let's just take this example, and let's say that something I considered doing and excluded it for the sake of a clear example was I was looking at what if this data was accessed from some API server living on JuliaHub, or what if it was a data set and you want to maybe generate new data and upload that new version so that the data set's updated. That's going to involve reading and writing to disk, and I think that's a perfectly fine trade-off in some cases, but sometimes that's going to bottleneck you, or that's going to become a limitation.
Yeah, and there is also a question about big data, which I think would usually be multi-file data sets, right? That's generally what people have. So in that case, I would do a parallel distributed loop over the files.
That was in the HPCR question, I believe, right?
Mm-hmm.
Yeah. And yeah, there's another question which came from Joseph. He says, have you tried using OpenAI or any other LLM to do the grunt work of partitioning and writing the code?
I have not tried that. I don't know if it could do that. That would be very impressive if it could do that. Maybe it can in some cases.
All right. And then from Yongzhen, he says, can you talk a bit about MPI and compare it with distributed?
So yeah, they're similar in that they're both distributed memory models. The API is just different. There is also an MPI package if you're used to MPI, or if that's available to you on your HPC cluster, you can just use the bindings we have to MPI. And so I would recommend that if you're used to it.
Absolutely. And then just to tack on, so some packages are going to have explicit extensions or support MPI. I've personally worked with this a little bit at JuliaHub, especially when we're doing some finite element work. MPI was advantageous for us to run on JuliaHub as opposed to some of the techniques we saw here, because I believe we were using Grid App, and it was pretty tightly integrated with MPI. And so, yeah, I think that's a good point, is if you're used to it, if the packages that you're writing or using make it easy to leverage them, then it can definitely be something to explore. And I do mention a couple of them in the white paper, but yeah, which package you're interested in is going to vary a lot. So I think that's good general advice.
Well, I like this question about where can I find the current vision, and what's a good way to start contributing. So check out the Julia Parallel GitHub org, github.com/JuliaParallel, where there are a lot of parallel related packages that are developed under there, or in the main Julia repo on GitHub, there are issue tags for parallel and distributed.
And there's another question from Prasanna. He says, I want to know if we need to do any optimization to get the performance benefits you mentioned. Like, does this use Intel optimized libraries or any other low-level optimization we need to be aware of?
Jeff, you want to take that one?
Let's see. So I assume, so like Intel MKL, for example, I don't know, is it available on JuliaHub?
I'm not sure.
I'm not sure if it is, but yeah, so we don't use MKL by default, but the default blast we have is pretty fast. It's very similar in performance. But you can use MKL if you want. There's a package for that will let you switch out the blast library. But you definitely don't have to just to get parallel speedups. You'll get parallel speedups even without that.
Okay, and the question is, can you use push function in parallel, or do we need to use shared array? Similarly,
oh, I did answer that. I did answer that one.
Okay, great. So
and
yeah,
but also I think push bang I don't think it works with shared array. Shared array really just lets it just exposes the shared memory POSIX shared memory segments. And actually the shared array type is kind of obsolete now. It was only developed before we had multi-threading, which was many years ago. So now I think there's no need to use shared array anymore. You can just use threads with normal arrays. But if you want to do mutations to them, you'll have to synchronize.
great. And we have a couple of more questions. One is the plotting in parallel still a problem if you are saving the plots to disk?
And the answer is yes, because it's during render, right? So like, for instance, when I'm doing the workflow that I just shared, I'm rendering the plot, and then I may display it to the plot window in VS Code, or I may just continue on execution, or I may save that plot at some later time. And so I think anytime that you are, my understanding is if you're rendered, if there's competing renders occurring is when you get into trouble.
Wait, and I think there's one more. I think Aryan wants the GitHub link to the repo you mentioned. So, is that
so I
that
did. I'm not sure if everybody can see the answer. I did post the repo to Scott's question. When he was trying to understand my final timings, it looked like the time had gone up. And I said, it's possible I made a mistake. I did post the repo there. I'm not sure if everyone is able to access that. It is, yeah, I don't know how to share through, because this isn't like.
Can we post it to chat?
Yeah, you can post the chat.
Okay, yeah, chat instead of QA. So yes, there we go. And I will. Oh, that's answered. Open. Yep.
Yep, and we'll also share this in the email. Actually, the recorded version of this webinar, along with this link, will be shared in the email with all the participants. Actually.
Yeah, that was my intent. I had a lot of links in my presentation. You're going to find many of those and more in the white paper and the blog post. And so, yeah, definitely plenty of room to dive deeper if you're interested.
You can. Are there any more questions? You can please type it in, and we'll take it in order it comes in. Let's just wait for a minute or so that in case anyone types in a question, we can answer them.
Thank you, Scott.
Okay, I see no other questions coming in. So shall we? Again, there's one. There's one from Joseph. Typically, a UI is single-threaded. I have been getting open AI to do the grunt work for. Okay, he just replying to a previous question. There's another question. Yeah.
Are you familiar with the parallel data transfer package? That seems like a good way to share data between different processes when using distributed. I am not aware of that package. Jeff, I don't know about you.
Yeah, no, I'm not aware of it either, but people have made a lot of good packages. So there is a bunch of good stuff out there, and it's there's now so much of it that I can't keep track of it anymore. But that sounds interesting.
It may be noise, but I know that at JuliaCon there's an interesting talk about around data toolkit, and maybe it also offers some of these same features. I'm not sure. So yeah, there could be several options depending on your problem space.
Okay, so we can check with Chris on this package actually. Chris. Right. Yeah, I see no other questions coming in, and we're over time as well. So shall we wrap up this session for the day? Yep. Thank you, everyone. Thank you for joining in, and thank you, Jacob. Thank you, Jeff, for this engaging session. And we'll email you the link to this recorded webinar along with the other GitHub repositories and resources that you can go through at your own time. And in case you have any questions, you can visit our website, drop in an email to us, and we'll get back to you. Thank you, everyone. Have a great day.
Thank you.
Thanks, everyone. Bye.
Bye.